Okay, so this lesson, we're going to start talking about triangles. And we're going to start with things that you're familiar with. So if you have, why is this on here? We don't want that. Okay, two triangles that have two equal sides are called what kind of triangle? Isosceles. And it's spelled isosceles, I-S-O-S-C-E-L-E-S. Isosceles.
Is that I or?
That's an I.
Pretty good. Sorry.
And then, if we have, here's a right triangle. Wow. That didn't work very well,
It's really
did it?
oriented board.
Well, I couldn't take my pencil up. Okay, when they have two sides that are the same, they also have two something else that's the same.
Angles?
Two angles that are the same. And then we're going to say that a right triangle that is also an isosceles triangle is a special right triangle. I'll try and draw a better one here. Okay. These two sides are the same. We know this is a right angle. How many degrees are there in a triangle?
180.
180.
Sorry.
And this one is 90, so that leaves 90 left for the other two. And since it's isosceles, we know that the other two are the same, so what do they both have to be? 45. So this triangle that we're going to talk about today is called a 45. That's a 4. 45, 90 triangle. Those are both 40. 45. There we go. That's all easy to read. 45, 45, 90 triangle. And what we're going to do is we're going to create them down here on this dot grid paper that you have. This is special dot grid paper. If the distance that this dot is from this one and this one is the same, those are both 1. The distance it is up or down from either dot is also 1. But is it 1 from corner to corner? No. And so, that's important. All right. Give me my pen back. Let's use it. Okay. The first triangle we're going to draw right here has a leg of 1 and a leg of 1.
Oh, sweeter.
You don't need your ruler for this part. You'll use that for your graph. You don't. It's really okay just to do it all in the same color. So each of these legs is 1, and we want to find the length of the hypotenuse. So I'm going to pull up another document. Yep. And we're going to make a table for the length of the leg and the length of the hypotenuse. And for this one, it has a leg length of 1. And then what do we know about using right triangles? And what? All those things that you said were true things about right triangles. A squared plus b squared equals c squared. The Pythagorean theorem will help us find the missing side. So a and b, remember, are the legs, and c is the hypotenuse. What are both of our legs? 1. So 1 squared plus 1 squared equals c squared. And 1 squared is 1. So 1 plus 1 equals c squared. So if 2 is c squared, then how do I find c? Take the square root. And so the square root of 2 is equal to c, the hypotenuse. And we'll talk about the estimation for the square root of 2 later, but right now we're just going to leave it the square root of 2. It's an irrational number. It is an irrational number. And so the length, now we know, if I go up and down, the length is 1. But if I go diagonal, what's my length? The square root of 2. Okay, now you're going to make your next triangle while I erase this and make it a leg of 2 each direction.
I have a feeling it's going to be positive. I have a feeling. Okay. Oh, can we draw it on top?
Yeah, you can just draw it right on top. And your new triangle has a leg of 2 this direction and a leg of 2 this direction. But then we need to know what the hypotenuse is for our chart. How far is it from this dot to this dot? Square root of 2. And from that dot to this dot?
Square root of 2. Oh, 2.
Square root of 2. So we have the square root of 2 plus the square root of 2. When you're adding the same square root, you just then have 2 times the square root of 2. Just like if I said 3 plus 3, could I also say that's 2 times 3? But since we know it's 6, we wouldn't. That's not usually helpful, but here it is because we don't, the square root of 2 is not a rational number. So we're going to say the square root of 2 plus the square root of 2 is 2 square roots of 2. So if there's a leg with length of 2, then the length of the hypotenuse is 2 square roots of 2. 2 times the square root of 2. Okay, and then let's do the third one. We're going to go 3 this direction and 3 this direction. So we want to know how many square roots of 2 we have. We have 1, 2, 3 square roots of 2. So 3 times the square root of 2. Okay, I want you to go ahead and draw as many of those triangles as will fit in this box and record the data in your table. Okay, you've finished doing that. So let's fill in the chart. When the leg length was 4, what was the hypotenuse?
4.
And when the leg length was 5, it was?
5 square root of 2.
And when the leg length was 6, it was?
6 square root of 2.
So do we see an obvious pattern?
Yes.
Yes. If the leg length was L, how could we find the hypotenuse? L times the square root of 2. And now what we want to do is we're going to graph all of this. Now that we're graphing it, now is when we need an approximation. The square root of 2 is about 1.4. So when the leg length is 1, the hypotenuse is about 1.4. If we have 2 times the square root of 2, what's that going to be? 2.8. And then 3 times the square root of 2 is going to be 4.2. And 4 times the square root of 2?
8.4.
No. 14 times 4. 5.6. That's 7.0, right?
Yeah.
And then 8.4. And now that we have these data points, we're going to graph them on the graph that you have on your worksheet. So here's your worksheet. We're going to put the leg length on the horizontal axis and the hypotenuse on the vertical axis. And we're just going to plot to the best of our ability. Obviously, we're going to be estimating a little bit because we're graphing decimals. If a leg length is 1, what's the hypotenuse?
1.4.
1.4. So we're going to plot that right in there. 2 gave us 2.8. Okay, my points are not looking good. You all keep going, and I'll see if I can make a better graph. You have your graph. You plotted 1, 1.4, 2, 2.8, 3, what?
4.2. 4.2.
4.2, 4.
5.6. 7.0.
Okay. And so what you notice is it does seem to be a straight line.
That was good.
And not bad. And where does it pass through? What's its y-intercept?
0.
0. Okay, so let's now look at the questions at the bottom of the page. We have our data, we've graphed it, we have something to look at. Now it says to write an equation to model the relationship between the length of the leg and the hypotenuse. And we said, how do we?
We can move the box.
No, how do we find the hypotenuse if we know the length of a leg?
How do you find the hypotenuse?
Yes, if you know the length of a leg.
Pythagorean theorem.
But how did we do it using our pattern?
Oh, we did.
Joy.
Well, can I make variables for the
Sure.
the leg is like x,
Mhm.
then it's gonna be x times the square root of.
Okay, so we did the length of the leg, whatever it is, if I say it's L, the length of the leg times the square root of 2 equals the length of the hypotenuse. We know we can use the Pythagorean theorem, but this shortcut seems to work every time. And I'll tell you, it only works for this special triangle. That's why we're talking about this one. Okay? And then the 45, 45, 90. And then the next question says, is this relationship an example of direct variation? And if so, what is the constant of variation? Now, you talked a little bit about direct variation last year in one of your chapters, so I'm just going to review you on what all of that means. There we go. So let's put this in your notebook. Direct variation is always in the form y equals a constant times x, where k is your constant of variation. Okay? So if we're looking at an equation and we want to know if it's direct variation, we look and see if it looks like this. Y equals a constant times our variable. It can look a little bit different. What if I want k by itself? What would I do to both sides?
Minus x. Divide by x.
Divide by x. So if I divide both sides by x, it cancels on the right and leaves me with k, but over here I'm left with y divided by x. These two are the same. They're just written in different formats. So if it looks like either one of these, then it's direct variation. How does it compare to y equals mx plus b? Helen? There's addition in the y equals mx plus b. Is there addition here?
No.
That's important. So what is the y-intercept here?
0.
0. So if it's direct variation, the y-intercept has to be 0. Manny?
Is the constant of variation also known as like the slope?
Well, when we're talking about it here, definitely, that's exactly where it comes into play, is the slope.
The other one? But is it indirect variation?
In direct variation, we call it the constant of variation, but when we're talking about the graph, then yes, it is the slope.
Okay.
So if we look back at our worksheet, does this look like direct variation?
Yes.
What is our constant of variation? The square root of 2 is our constant variation because we have y is our h equal to a constant times x. So we write yes, and the constant of variation, k, is equal to the square root of 2.